Oh, anyway, I see it's high noon, so welcome back, everyone. So as you'll recall, last time we ended off with, beginning in chapter 7, I would say, we discussed structure and nomenclature of alkenes. We went through the whole cis-trans system, which is fine, except that it only applies to certain di-substituted alkenes. And as soon as you get to a tri or tetra-substituted alkene, game over. Cis and trans no longer works. So that's where the E and Z system comes in, and we learned how to apply that. A couple of other things in that area, by the way, maybe before I get into the new material. One thing I should also mention is if you have what we call a geminal disubstituted alkene, and we'll introduce all these terms later, actually, but meaning that you have two of the same group on either of the two alkene carbons, doesn't matter which. And it doesn't have to be two hydrogens. If it's two methyls, two ethyls, two chlorines, but as soon as you have two of the same on either or both of the carbons, game over. It's neither cis nor trans, neither E nor Z. And I think that's pretty evident if you think of a molecule like, I don't know, 2, 3, 4, 5. We'll make that a hexene. So something like this. Well, this carbon over here has two methyls on it. So there is no cis or trans. There is no E or Z. We just would call that what? It's 1, 2, 3, 4, 5, 6. I propose we call that 2-methyl 2-hexene. No cis trans, no E and Z, because it's not possible. How could there be? Anytime you compare two groups that are the same, well, by definition, it's a tie. So there is no cis and trans, there is no E and Z. And you'll run into that sometimes. The other thing I also forgot to say is cis-trans is the older system by far. Although it's limited in use, E and Z came along later. But I should mention that whereas you can't always use cis and trans, you can always use E and Z. So if you wanted to call cis-2-butene Z-2-butene, you can. Absolutely, completely acceptable. And if you wanted to call trans-2-butene E-2-butene, you certainly can. It's absolutely correct. Nothing wrong with it. So, but I think those were really the only other things I meant to say about cis-trans and EZ. What we need to get into next is some more about the properties of alkenes, specifically regarding molecular structure, because we're, oh, I'm sorry. Oh, I should have left that up there. Oops. Okay. Diene or triene? I mean, if you phrase the question that way, so I can't wiggle out, I would say no. I would not take off points for either new or old system. I don't really care what you use. Yeah, I think I think they are equally correct. Yep. You mentioned last week that there was a worksheet or something on eCampus that would help explain reaction mechanisms. It's in the chapter 6 class notes. It's basically meant to be kind of a guide. It doesn't go through every single possibility, but it's meant to give some ideas of how to know whether you're drawing mechanism arrows correctly. But it should be included in the chapter 6 class notes. At least last I checked it was. Okay, other questions then. Okay, so one issue that I promised to put off till today, since I really didn't want to end the last class with it, because I wanted to make sure we had plenty of time, was this issue of degree of unsaturation, also called index of hydrogen deficiency. And there you go. Once again, two names for the exact same thing. So I don't care which term you use. You can mix and match. I've heard, you know, degree of hydrogen deficiency, or, you know, mix and match. Any of those terms is all fine. So you didn't see that in the chapter 6 class notes, because I thought I had included in the class notes. But I will check when I get back to my office around 1:15, and I will make sure that it's available in some form in the section of eCampus where your class notes are. If it's not there, then I'll make sure it's added. I guess we're done. Okay. Right. So the reason that you need to know about degree of unsaturation is because you'll run into times very frequently where you know the formula of a compound, but you don't exactly know what its structure is. And one thing you need to be aware of is just because we know the formula, that doesn't mean that any old structure is possible. Our possibilities are limited. Just having a formula doesn't mean there's an infinite number of possible structures. It's finite. And not only that, but it's also possible to come up with a formula that's impossible, that doesn't correspond to any structure, like CH8, to give a really obvious one. So the reason you need to know the relationship between structure and formula is because later on, we're going to be doing problems that involve working out the formula of a molecule, especially when we talk about spectroscopy. So this will happen next semester as well. But you work out the formula, and then you need to figure out what the structure is. And it's very helpful if you can limit your possibilities, because otherwise it looks at first like everything is possible, but it isn't. So the degree of unsaturation tells you the relationship between the structure of a molecule and its formula. That's basically what it's for. And so when you're asked about structures given a formula, it limits your possibilities, because it makes you understand that the possible answers are not infinite in scope. There's only finite possibilities. Now, I'm going to introduce the idea at first, just considering hydrocarbons. We will get to the point pretty soon, I mean in this class, where I'll have to read that in just a moment, but where we're going to get to the point where we also consider heteroatoms. The most common heteroatoms, of course, being halogens, oxygen, and nitrogen. And we'll learn how to, there's a Y over here, hydrogen deficiency, there you go. And we'll learn how to deal with those as well. There is also, I should mention, a formula in the book that takes all of the heteroatoms into account. You just plug it in and out pops this number, which is your index of hydrogen deficiency. You can memorize that formula if you like. I've never bothered. I'll show you the method I use, which involves, if you're given a formula that has atoms other than carbon and hydrogen in them, you kind of convert the formula to the formula of an equivalent hydrocarbon. And then you can figure out the index of hydrogen deficiency fairly easily. So another way to define degree of unsaturation, here's another definition, is it's the number of rings plus pi bonds in the molecule. That's another definition of degree of unsaturation. And again, it doesn't tell you the number of rings, and it doesn't tell you the number of pi bonds. It only tells you what the sum of rings plus pi bonds is. That's the best you can do. But it's still, as you'll see, quite a bit of information. It really limits the possibilities. And the reason that this definition holds is because every time you form a ring or a pi bond, you need to take away two hydrogens in order to do that. And I think you can see that's the case. Consider going from hexane, which is C6H14, to cyclohexane, which is C6H12. You needed to take off two hydrogens in order to be able to connect the ends into a ring. And if you wanted to connect into a 5-membered ring, you'd still have to take away two hydrogens. Meanwhile, if you wanted to form a pi bond, consider going from ethane, which is C2H6, to ethylene, which is C2H4. You have to take away two hydrogens in order to make the pi bond. And that goes for larger molecules too. It doesn't even matter if the pi bond is between carbons. You can make triple bonds that way. A triple bond will just count as 2 pi bonds, so it will take up 2 degrees of unsaturation. But that's always going to hold. You will find there are no exceptions. In order to form a pi bond or a ring, you must take away 2 hydrogens. Good. So that's basically how this definition works. It gives you, it tells you the possibilities for your structure, and it limits your field for your structure. Only certain structures are possible. This is not the only correct way, but this is a formula for a hydrocarbon. So you have a compound with only carbon and hydrogen. This formula, where N is the number of carbons in the molecule, will give you the degree of unsaturation. And I should mention, you should always get a whole number, meaning an integer 0 or higher. So if you get a degree of unsaturation of 3.5, you did something wrong. It should always be 0 or 1 or 2 or 3, etc. And the way this works, you might remember talking about 2n plus 2. That was something we talked about in an earlier chapter, where n is the number of carbons, 2n plus 2 is the maximum possible number of hydrogens you can have. In other words, the formula of a fully saturated acyclic alkane, so no multiple bonds, no rings, is CnH2n plus 2. And that's a good little formula to stick in the back of your mind. I'm not normally a huge fan of memorizing formulas, but that one's probably not too bad. And so that's the same 2n plus 2 here. And what this formula tells us is you figure out that maximum number of hydrogens that could be in the molecule with n carbons, and then you subtract the number of hydrogens that actually are in the molecule, and you divide the whole thing by 2. And that will give you the index of hydrogen deficiency, or the degree of unsaturation. And we'll do some examples here, and we'll show how you can learn something about the structure of a molecule from its degree of unsaturation. But again, this is only going to be for a hydrocarbon. I'll show you pretty soon how I deal with heteroatoms. And again, there's a bigger, uglier formula that includes other atoms in there. And if you want to memorize that, you can, but I like this way better. So N is the number of carbons in the molecule. And you can see how this is going to work. If the compound is in fact an acyclic alkane, like hexane, well, hexane is going to have 2n plus 2 is 14 hydrogens. It's C6H14. You subtract from that the number of hydrogens that are there, which is 14. 14 minus 14 is 0, divided by 2 is 0. So your index of hydrogen deficiency is 0. And that's going to be the case for a saturated acyclic alkane. But otherwise, there will be fewer hydrogens in that. And we'll look at some examples of all of that. So let me show you how you can use this formula to figure out the degree of unsaturation, and from that learn something about the structure. To give an example of what we were just talking about, we'll say C3H8. Well, N is 3, because there's 3 carbons. 2n plus 2 is 2 times 6 plus 2, which is 8. And then you subtract the number of H's, which is 8, and you get 0. So, and in fact, I think there's only one way to put together 3 carbons and 8 hydrogens, propane. So that's the only way you can put that together. So actually, we're limited to just one structure there. What about one that's a little more interesting? What if instead we had C3H6? Well, again, N is the number of carbons. 2 times 3 is 6. 6 plus 2 is 8. We'll subtract the number of H's that we actually have, which is 6. 8 minus 6 is 2. 2 divided by 2 is 1. So that's a rather scary looking 1. But anyway, that tells us that we must have either a ring or a double bond, or a pi bond, I should say. And in fact, I think we're limited even beyond that, because it seems to me that for C3H6, there's only 2 possible structures. You can have propene or you can have cyclopropane, and that's it. I don't think there is any other C3H6. But both of those, if you examine them, you can figure out the formulas for yourself. You'll find they're both C3H6. Let me do some slightly bigger ones. Let's do C5H8. And again, we're starting here with hydrocarbons. We'll get to what happens when there's heteroatoms pretty soon. So let me see. 5 times 2 is 10. 10 plus 2 is 12. 12 minus 8 is 4. 4 divided by 2 is 2. So the index of hydrogen deficiency is 2. And I'll even say in the exam, if you want to bring a calculator, if you need to calculate any of these, you can. I don't think you'll really need it, but at the same time, I would feel terrible if someone got something wrong just because they didn't use a calculator. But our degree of unsaturation is 2. And what that means is there's either 2 rings or 2 pi bonds or one of each. And that still gives quite a bit of leeway as to what the structure of the product is. You could have something like, say, or the structure of the compound. You could maybe have something like cyclopentene. That is a ring and a pi bond. That should be C5H8. You might have 1,3-penadiene. That should also be C5H8. Can we make a compound that has 2 rings? I think we can. It look kind of like a house and be stupidly strained. I'm sure that compound's known and has been studied. All of that stuff was studied back in pretty much the 50s and 60s. But the point is, whatever the case, all of those should be C5H8, and you can verify that on your own. So again, the degree of unsaturation doesn't tell you the number of rings, and it doesn't tell you the number of pi bonds. It tells you what the sum is of rings plus pi bonds. And that still limits your choices quite a bit. It means that if you're given a formula, the possibilities aren't limitless for what the structure can be. You have limits placed in the structure. Let me do one more that's maybe a little bit bigger. What about C11H18? So 2 times 11 is 22. 22 plus 2 is 24. 24 minus 18 is 6. 6 divided by 2 is 3. So that means we've got a grand total of 3 when we add up rings and pi bonds. So can I actually make up something with, I think I'll start with just pi bonds. You know, we could have, for instance, a triple bond. And maybe I'll put another pi bond at the very end. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And I'll put another pi bond out there. That should be, wait a minute, do I have, yeah, that's 3 pi bonds. So that should be C11H18. What can we maybe do with rings? Let's see. I'm sure we could get something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9. I need 2 more carbons. Oh, we'll just put 2 methyl groups up here. That should do it. But yes, the triple bond counts as 2 pi bonds. And that's because that's how a triple bond is defined. 1 sigma bond and 2 pi bonds. So there's no contradiction. It works out with the definition. So that thing should have 11 carbons. I have only 2 rings, so we need a pi bond somewhere. Might as well put it there. That should be C11H18. And again, you can verify that for yourself. But any combination of pi bonds and rings is possible. And when we start introducing heteroatoms, you can have them involved in the multiple bonds. Like if there's an oxygen in the molecule, you could have C double bond O. That would count as a pi bond. So, but I think that gives you, I didn't really mean to go 0, 1, 2, 3, but it turned out that way. So that I think gives you some idea of what you can do once you know the degree of unsaturation. It's pretty powerful, actually, because at first glance you think, here's a formula. What is, you know, the structure can be anything. Well, no, it can't. There's significant restrictions on what the structure can be. Any questions then on hydrocarbon cases? And again, you'll see examples of questions involving this in OWL. I've also posted an old exam. So that will give you some ideas as well. But does that kind of make sense? Everyone clear on at least the special case of hydrocarbons? All right, well, let's consider then heteroatoms. And I think you'll agree the most common heteroatoms by far for us are going to be halogens, chlorine, fluorine, chlorine, bromine, iodine, oxygen, and nitrogen. Oh, you might get sulfur, but probably sulfur is going to be kind of like oxygen, you know, unless you've got some weird sulfoxide or something like that. If it's a normal sulfur in the -2 oxidation state, it'll be just like oxygen. So I think as long as we know how to deal with oxygen, we're pretty well prepared. And the other possibility is nitrogen. Those are the three most common heteroatoms by far. I think you'll agree. Even talking about biologically related molecules. So let's consider halogens first. Very simple, each halogen counts as a hydrogen. Pretty simple, right? And that makes sense because halogens want to form one bond, at least in order to the formal charge of 0, which we would hope it would have. So you can just, for each halogen, you can throw it out of the structure of the formula and replace it with a hydrogen. So just replace all halogens with hydrogens and you will get an equivalent formula. So for instance, if we're given C6, that's a 6, though you'd never know it, H8F2. Well, that's going to be the equivalent of C6H10 because the two fluorines take up the same space in terms of bonds as two hydrogens. So these will have the same index of hydrogen deficiency. C6H10 looks to me like it'll have a degree of unsaturation of 2, right? C6H4 would be, 14 would be fully saturated. 14 minus 10 is 4. 4 divided by 2 is 2. So that one would also have a degree of unsaturation of 2. So halogens are pretty easy to deal with. They just replace hydrogens. And yes, you can use that formula that's in the book. I never bothered learning it. I just do it this way. I think it's easier. If you find it easier to use the formula, go right ahead. By the way, please also register your attendance. I will have a REEF session later, but it will not be for polling. So it will not show up on REEF. I just have a little exercise for you guys to work on, but I'll just take attendance today. What about oxygen? You're going to like oxygen even more. Oxygen has no effect on degree of unsaturation. So you can effectively just throw them out of the molecule. That's a little sloppy. Let me see if I can do a little better. Degree of unsaturation. Throw them out of the formula. They have no effect. And I think that makes sense because oxygen is 2 bonds. So you can imagine just pulling the oxygen out and then connecting up the 2 bonds to the things that were attached. And you will get an equivalent molecule without changing the degree to which it's unsaturated. So if you had something like, I don't know, C4H2Cl4O2, that would be the same thing as C4H6. This is a 4. Because the 4 halogens take the place of 4 hydrogens, and the oxygens have no effect on the degree of hydrogen deficiency. So it comes out as the same as C4H6. If this were fully saturated, it'd be C4H10, right? 4 times 2 is 8, 8 and 2 is 10. 10 minus 6 is 4, 4 divided by 2 is 2. So both of those formulas have a degree of unsaturation of 2. So oxygen's real easy to deal with. You just ignore it when you're calculating degree of unsaturation. Last but not least, for nitrogen, it's a little more complicated than oxygen. And that's because nitrogen's weird, it's 3 bonds. So for each nitrogen, the way I like to think of it is throw out NH from the formula. And again, the reason that each nitrogen has to take a hydrogen with it is because it has 3 bonds to oxygen's 2 bonds. And that hydrogen may or may not be directly bonded to the nitrogen in the actual structure. But in order to remove the effect of the nitrogen on the degree of unsaturation, it has to take a hydrogen with it. And again, if you look at that formula in the book, you'll see that basically they account for that in the exact same way. But again, because nitrogen is 3 bonds to oxygen's 2, you can't just throw the nitrogen straight out. Each nitrogen is to take a hydrogen with it when you throw it out. And then you'll get an equivalent formula. So for instance, if we had, let's say, C7H12 Cl2N2, a million. It can have however many oxygens you want. Well, that's going to be the same thing or equivalent to C7H14, but then for each of the nitrogens, you have to throw out a hydrogen with it. So we go down to 12 hydrogens because the chlorines both count as hydrogens. So at first it's C7H14N2. Then each of the nitrogens, you throw out a hydrogen with it, and you get back to C7H12. So if this were saturated, it'd be C7H16, because 7 times 2 is 14, 14 and 2 is 16, 16 minus 12 is 4, 4 divided by 2 is 2. And again, I wasn't trying to make them all turn out to be 2, but they did. So, but you can, so in any case with this formula, you would find you have to have either 2 rings, 2 pi bonds, or 1 ring and 1 pi bond. And in cases where you have, let's say, oxygens and nitrogens, you can, if you have any pi bonds, they can involve the heteroatom, right? You can certainly have C double bond O or C double bond N. That's allowed. That counts as a pi bond too. But in any case, once you know the degree of unsaturation based on the formula, it significantly limits the possibilities of the number of structures you can draw, and just makes the whole thing, I think, much less complicated. So that, I think, is basically the point. I don't know that I have time for any more examples, but is everyone clear on degree of unsaturation? Any questions on any of that? And like I said, you'll get an idea of possible question formats and so forth from OWL and from my past exams. But you'll get to practice this on OWL for sure. So let me see. My goal, since we already covered pretty much nomenclature, E and Z, my plans for today is I want to talk about relative stability of alkenes. That's going to be important because that's going to help us to predict what's going to happen when we react a given alkene with a given set of reagents. And that's going to be chapter 8. Chapter 8 is going to be all about electrophilic additions to alkenes. So it's going to be a lot of reactions to learn, but they're all going to have that one thing in common. But it's going to matter a great deal what type of alkene we start with in terms of how reactive it is, and that will give us information about the type of products that we'll get. So that's why that's important. As I said, I also have a little exercise for you guys just for a few minutes on alkene addition reactions. We only know of one so far, hydrohalogenation, but we'll just get in a little practice on that. And then we'll end off with the idea of how does the structure of the starting material, the starting alkene, affect what the products are. And then that'll be a good ending point. We can leave Markovnikov's rule for next time. Good. So let's see, maybe I could start even with just something simple like cis-2-butene and trans-2-butene, or if you will, Z2-butene and E2-butene. You can call them that also. It probably would come as a surprise to no one that the trans compound is more stable than the cis compound. And the difference is not huge, but it matters. The difference in energy between the two is something like 2.8 kilojoules per mole. Of course, I don't care if you memorize that number. I only know it because I just taught on this less than an hour ago, and I remember it from back then. By tomorrow, I'll have forgotten it. So again, it's not a huge amount, but it's a noticeable amount. And the reason is in the cis compound, you've got a significant amount of steric strain. Back to that again. We defined steric strain a couple of chapters ago. It's all of these hydrogen atoms, all of these carbon-hydrogen bonds on these methyl groups. All of the electrons in those bonds are going to bump into each other in the cis compound because we can't rotate around that double bond and the molecule is planar. And that steric strain interaction is relieved in the cis compound, in the trans compound. So that's going to explain some of the properties of the order of alkene stability. That's one of the factors, is steric strain. But then there's another factor, which is simply the inductive effect, meaning that alkyl groups can donate electron density inductively into an adjacent pi bond if you have alkyl groups on an alkane. And that's going to lower the energy because the pi bond is essentially a big electron source or electron sink. And if you can have electron density around the pi bond, that's going to stabilize the two carbons that the pi bond is between. So those two effects are going to dictate the order of stability. And besides that, the order of stability of alkenes is going to be important for you guys to know, as I said, going into a big chapter on reactions of alkenes. So let's see, we'll call this order of alkene stability. And should you memorize this? Probably, possibly. It might not be necessary. I think the order kind of makes sense based on what we just said, that the two properties that affect it are going to be the inductive effect of surrounding alkyl groups, and also this issue of steric strain, which again we defined back in chapter 2 or 3, maybe 3. So, so it's a mixture of those two things. The least stable alkene of all is going to be ethylene. Correct. Slightly more stable than ethylene will be a monosubstituted alkene. Because again, the presence of this alkyl group stabilizes the two alkene carbons. It makes it easier for them to bear having that double bond with all its electron density, because the R group is helping to spread out that region of electron density. So this is monosubstituted. And then you'll think there's cis and trans, so that's 2. There's actually 3 flavors of disubstituted alkenes, one you might not have considered. The least stable of those is going to be where the 2 alkyl groups are attached to the same carbon. And I think you'll agree there's the most steric strain here because they're right on top of each other. That's even worse than if those 2 R groups were cis. And of course, R1 and R2 can be either the same or different. We call that kind of substitution geminal disubstitution, Geminal. I don't know the source of that word, but that's all I've ever heard them called, geminal disubstituted alkenes. Next higher in stability will be your cis disubstituted alkene, or if you will, Z disubstituted. And then after that comes the trans disubstituted alkene. That relieves that interaction that causes steric strain. And then after that point, the inductive effect starts to take over, starts to become more important than the effect of steric strain. And as we add more alkyl groups, we stabilize that double bond further. So the next possibility is the tri-substituted case, where there's 3 alkyl groups. Again, they can be the same or different. and 1 hydrogen left. So that's tri-substituted. And then last but not least, you've got your tetrasubstituted compound. That's your most stable kind of alkene. And certainly you'll find examples of questions that ask you directly about this in OWL, and possibly in my old exam. But later on, this is really going to matter for us. It's going to help us to be able to predict what will happen in a reaction, and certainly to predict what's going to give the most favorable outcome, the most stable product, given that we know something about the starting material as well. So this is going to be useful information, not just in the immediate future. We're probably going to refer back to this in later chapters as well. But I think you'll agree this order, I think, kind of makes sense, given that those two effects are what hold sway here. The effect of steric strain and the effect of the inductive effect on stabilizing the alkene pi bond. So that's basically it for that. That I think will at least be enough to get you started. Any questions on that order of stability? Don't tell me I did it again, that I'm such a good teacher and that was so clear that no questions were possible. Give me a big ego. Okay, well, let's leave it at that. And of course, this will be on YouTube. So, hi, YouTube. Let's then move on to, well, this will be easier with a mouse, won't it? Let's move on to our clicker session or our Reef session. And again, nothing's going to show up on your Reef app. This is just attendance. So if you haven't registered your attendance, please do so. But I have a little exercise for you guys that I think is timely, will get us into the next topic, and even refers ahead to some of the material from Wednesday. So your mission, should you choose to accept it, which by being in this class, you have tacitly chosen to accept it. When trans 3-hexene is treated with HBr, only one product is possible, ignoring stereochemistry. So don't worry about RNS. Write the mechanism of the reaction. And then I think already you ought to be able to answer the question, why is only one product possible? Carbocation rearrangements we'll talk about next time. That's going to be one of the last topics in the chapter. Though if you've read ahead, you might want to consider that, and I'll certainly address that here. But we're mainly going to cover that the next time. But even right now, that should be a mechanism I would expect you to be able to draw, and and I expect you to be able to determine what the major product is. Another thing, looking ahead on our calendar, if I'm not wrong, our next exam is a week from today. So yes, Monday, October 5th, so a week from today. So hopefully this will go somewhat more smoothly than the last time. Part of it was my fault. I just significantly underestimated how difficult it was going to be for me to keep track of who's taking it online and who's taking it in person. The practice exams are all already posted for all 4-hour exams. There will never be a practice exam for the final exam. We traditionally in this department don't post it. The other professors also don't post those, but you will have practice exams for all 4. Good, so hopefully that goes a little bit better this time. I think it will, because what I'm gonna say is if your status is going to change for the second exam compared to the first, then you should email me. In other words, if you took the first exam online but want to take the second exam in person, or you took the first exam in person and you want to take the second exam online, then please let me know. Please email me. But if you're going to do the same thing that you did with the first exam, you don't have to bother to email me, because I have all that information now. I have the list of who was online and who wasn't, so hopefully that will all work out fairly easily. That also reminds me, I did everything over the weekend that I said I would do. I put up the document that shows you how to calculate your class grade and also how to calculate what you need to get on future exams. That's available on eCampus. And I also used the method in that document to post estimated course grades at this point for everyone. Again, it's kind of a stretch. I'm assuming that you get exactly the same as you got in exam 1 on exams 2, 3, and 4, and an equivalent score out of 200 on the final exam. Like I said, that's kind of a stretch. I don't think anyone's ever that consistent. But I used the same method, and I came up with a number out of 1,000. And like we said, 900 and up is an A, 800 and 900 is a B, 700 to 800 is a C, and so forth. So that's all there. I would say take a look, certainly work it out yourself. If you come up with something very different, probably you should let me know. I don't think I've made a mistake, but it's always possible. It's been up there a few days, and I think if there were widespread mistakes, I'd have 500 emails. So I think it's probably okay. But, you know, still, if you get something very different, let me know, or stop by office hours. That'd be fine. I'm going to use those grades for midterm grades. I unfortunately have no choice. This happens every semester. The second exams will never be graded in time before midterm grades are due. So if you get a midterm grade, it should be the same as whatever you see there. But like I said, I don't put much stock in grades at this point. It's only been one exam. So, but do take a look. Okay, so here's how I drew it. And here's how I drew it under the limitations of ChemDraw, which it doesn't always allow me to draw arrows exactly the way I would like, but I would say what you see here is acceptable. And if this were on an exam, it would receive full credit. And everything shown needs to be shown. Anything not shown is okay not to show. But hopefully this reminds you very much of what we did last time. We start with our alkene in the, why is that red? Anyway, in the first step, looks like a laser pointer. Anyway, in the first step, our alkene is going to be our Lewis base, or our nucleophile. That's going to react with HBr, which is not only a Bronsted-Lowry acid, but also a Lewis acid. And it's going to pick off H plus from the acid, because that's what acids do, right? They give up H plus and release the halide ion, in this case, bromide. And so you get this carbocation. And again, the reason that you only get one product is because you only get one carbocation. It would be good, it would be worth your time. It would not be wasted time if you convinced yourself that if instead we'd put our HBr over here and had the double bonds shift out that way, you would get the same thing. It's the same carbocation, whether the plus charge is here or over here. But that would be a good thing that would be a good use of your time to convince yourself that either way you get the same thing. And the reason is the alkene starting material is symmetrical. So there's only one possible carbocation intermediate. Once you get that, then we have a second step in which the halide ion, in this case bromide, attacks that carbocation, and then you get the product. So like I said, everything shown here needs to be shown. Anything not shown is okay not to show. Remember, this reaction takes 2 steps. This does not happen all at once, but it's been experimentally proven that this type of reaction is 2 steps. First, the addition of the proton to the alkene, or the addition really of the alkene to pick up the proton from the acid to form this carbocation intermediate. That has been experimentally determined to be an intermediate in this reaction. And then subsequently, our halide ion attacks and you get the product. So yes, if you tried to draw that all in one step, you would lose points. That would not be correct. This should be fully consistent with what we covered in class the other day. Now again, you may not be asked to show the mechanism. It might just say, show the product. Then you don't have to show the mechanism. So I think you know the rules for that. You have to do everything it says. You don't have to do anything it doesn't say. But if you do have to show the mechanism, then yes, it should at least be the equivalent of what you see here. It doesn't have to look exactly identical to that, but it should be the equivalent of that. So let me see where we are in terms of time, 12:45. Looks like I have 5 minutes. So that's going to be enough time, I think, to wrap it up. Yes? Mm-hmm. And it remains attached to one of the carbons when it splits off. And that's the carbon that the H will become attached to. The other carbon will have the plus charge. Well, because you're swinging away an electron pair from it. You're taking electrons away from it to attach the H to the other carbon. Neither. It's remaining attached to the fourth carbon. I'm showing it kind of swinging like a hinge, like you're doing. Yes. And when you do that, it breaks away from one of the carbons. And the way you know that it breaks away from that one is because of where we put the H's. So over here, I didn't draw the H's on this carbon, but that's a CH2. One of those H's was there to begin with, the other we just put on. The carbocation, what? I'm sorry? Right, yeah, the carbocation carbon still has this hydrogen that was there to begin with. That's still there. You could draw those H's if you find it easier to see, but when you're using line angle drawings, they're understood. So, yes, but like I said, if we instead swung the double bond out that way and picked up a proton over here, that would put the plus charge here, but it's the same thing. So not only would I not take off points, I wouldn't even notice. It's the same thing. Nope. No, the carbocation is the carbon that does not get the proton because it uses that electron pair, whoops, to pick up the proton. So, and like I said, it doesn't have to look exactly like that. Anything equivalent to that would be fine. Good. Where does that leave us? 3 minutes. Good. So this is all fine. This is an example of starting with, oh, sorry, let me answer all the questions first before I go on. Yes. Oh, I would think it would look, the energy diagram I would think would look just like what we had the other day. I would expect it to be anyway. Good, other questions then? Right, and again, that's fine as far as it goes. Let me just switch us back for these last couple minutes to the whiteboard. This is an example of what happens when the starting alkene is symmetrical. We could have taken, also say something like, I don't know, what about cyclopentene? That's symmetrical also. There's a plane of symmetry running right down that. And let's say we treated this guy with HI. And let's say the question said, draw the product and show the mechanism. Well, it would start out the same way. You would swing out the pi bond to pick up H plus from HI. And it doesn't, you don't have to put the HI here. You could have put it up here, you know, it's the same thing. See, that's the key to this when the starting material is symmetrical. So since we swung the bond down here and away from this carbon, that tells me that that carbon's going to have the plus charge. And like I was saying to the other student just a moment ago, if you want to draw these H's, if that makes it easier for you to see what's going on, go ahead. It's absolutely acceptable. You just don't need to draw the H's when you're using line angle drawings because they're understood. But you get this intermediate, the carbocation, and then our halide ion attacks that carbocation, and you get iodocyclopentane. And here even stereochemistry is a moot point because that carbon's not chiral. There's a plane of symmetry running down the molecule. So, but that would be the only product possible. So that's all fine, but what if the starting material is not symmetrical? What if instead of cyclopentene, we had 1-methylcyclopentene and treated this with HI? Are we going to get that? Or are we going to get that? And that's something that we need to use Markovnikov's rule to determine. So that's going to be next time. Next time, Markovnikov's rule. M-A-R-K-O-V-N-I, Markovnikov, K-O-V. There's other, sometimes they use double F instead of the V's, Markovnikov's rule. That's what we'll use to help us out in cases when the starting material is unsymmetrical. So that's next time. It's going to turn out to have to do with carbocation stability. So I'm out of time, so I'll see you all on Wednesday.